This is the second part of my lecture on non-parametric tests. I'm going to be talking about tests for comparing a sample and the population with a known mean. The test that we're going to be using is Wilcoxon's signed rank test. It's a single sample test that only requires one sample of measurements, but it does require quantitative data. We have to have numbers which must at least be on an interval scale, which means we can take differences, because the test requires us to take the difference between two numbers. But we don't require the data to be normally distributed, so we don't have that requirement which would be necessary for a parametric test. This is a non-parametric test. It doesn't care about the shape of the distribution. But the test is used to compare a sample with a population when the population mean is known. So let's assume that we know the population mean, which we'll call MP. Now, our null hypothesis is that the measurements in our sample have the same mean MP, that is, they are distributed symmetrically about that mean. It doesn't matter what the shape of that distribution is. If the mean is MP, then they are equally distributed either side of that. So we take the difference between each measurement and MP. Some differences will be negative because the value is less than the mean. Some differences will be positive because the measurement is greater than the mean. But if the null hypothesis is true, then we expect an equal distribution of positive and negative differences. That is, they're equally distributed above and below the mean. So that is what the test is all about. The steps in the calculation of the test are quite straightforward. First of all, we subtract the mean, MP, which we know, from every measurement. That creates these differences. Some of them are going to be negative and some are going to be positive, depending whether the value was above or below MP. Then we rank the differences in order, but in doing so we ignore the sign for the moment. So we just use the magnitude of the difference, not the sign. However, if any differences are exactly zero, that is, the measurement was exactly equal to the mean, then we ignore it. Then we have to adjust the ranks for any ties by the method that I showed you in the first part of this lecture. Then we sum the rank of all the positive differences, and we sum the rank of all the negative differences. And if the null hypothesis is true, then the sum of the ranks of the positive and negative differences will be similar, because there are just as many above the mean as there are below the mean. So, to test whether this is significant, we compare the smaller of the two rank sums with the critical value which we can look up from tables. And if the rank sum is smaller than this critical value, then the null hypothesis can be rejected. Now we have to be careful there, because in most tests, if we have a test statistic that is greater than the critical value, then we reject the null hypothesis. But in this particular test, because we're taking the smaller of the two rank sums, the null hypothesis is rejected if the rank sum is less than the critical value. So just be careful about that. This is slightly different to most other tests. Here's an example using DMSA scans. Let's suppose we want to know, do left and right kidneys have equal function on average? Well, we might suppose that they do, and if it's true, if they are equal, then each would have a relative function of 50%, because left kidney would be 50% and right kidney would be 50% of the total function if they're split equally between the two kidneys. So the hypothesis that we want to test, the experimental hypothesis H1, is that the relative function of the left kidney is not 50%. And the null hypothesis H0 is that the relative function of the left kidney is 50%, at least on average. That's a two-tailed test, because we don't mind whether the left kidney is below 50% or above 50%. That will disprove our hypothesis. Note, we're only using the left kidney for convenience. We could equally well have taken the right kidney, because of the hypothesis that they're equal. It doesn't matter whether we look at the left or the right. Here's some data. Let's suppose we've got measurements of the percentage relative function of the left kidney from 10 patients who had DMSA scans. And we got 40%, 32%, 50%, 5%, 55%, 38%, 69%, 38%, 18% and 62% from these 10 patients. This is hypothetical data that I've made up for illustration purposes only. So here's what the data would look like. Here on the vertical scale we've got the relative function of the left kidney with a line at 50%, which is our assumed mean, and I've plotted the value of the 10 measurements there. Do you think those look like they're typically around about 50%, or do you think the average is somewhat less than 50%? That's basically what we're asking ourselves. Well, we've got one sample of data and a known population mean. Our 10 measurements are the sample. The assumed mean of 50% is the assumed population mean we want to compare with. The data are certainly quantitative. We've got numbers in each case. And if it was normally distributed, then we could use the one sample t-test. That's the test that we talked about in the previous lecture of a parametric test for comparing a sample with a known population. So if we look at that and we think those are normally distributed, then we'd be quite happy to use the t-test. Actually, here I think the data are probably quite strung out and uniformly spread between 5 and 70. So there's no sort of peaking at the centre, which would make it like a normal distribution. So although you might get away with a t-test in this case, let's be cautious and assume that they're not normally distributed, so we'll use a non-parametric test. And the non-parametric test that is appropriate here is Wilcoxon's signed rank test. So here's the data we're going to use. Here are our 10 patients, numbered 1 to 10, and the relative function of the left kidney I've shown here 40%, 32%, 50%, 5%, and so on. If you remember, the first step of the calculation was to subtract the assumed mean, which in this case is 50% from all of the measurements. So 40 minus 50 is minus 10, 32 minus 50 is minus 18, 50 minus 50 is 0, and so on. Then we need to separate these numbers up into the sign and the absolute magnitude. So minus 10, for example, has a negative sign and a magnitude of 10. Minus 18, again a negative sign and a magnitude of 18. 0 is just 0 with no sign. And so on. We've got minus 45, which is negative, 5, which is positive, minus 12, which is negative, and so on. The next step is to arrange these into increasing order of magnitude, ignoring the sign. If we look at the data, patient number 3 is the smallest with a 0 difference, and then we've got patient 5 who has a difference of 5, followed by patient 1 who has a difference of 10. So here I've arranged the same patients into increasing order of magnitude, starting with patient 3 with 0 difference, patient 5 with a plus 5 difference, patient 1 with a minus 10 difference, and so on. So in ordering them, I've kept the sign and the magnitude together, but the order is based on the magnitude column, ignoring the sign. Now we have to rank the numbers in order, but for this purpose we ignore any 0 differences. So this 0 is not included in the ranks, and rank of 1 is given to 5, a rank of 2 to 10, 3 to 12, 4 to 12, and 5 to 12. The rank of 1 applies to patient 5 who had a positive sign, so I put that rank in the positive sign column. The rank of 2 applied to patient 1 who had a negative sign, so I put their rank in the negative column. Then we get to 3 patients who share the magnitude of 12. Patients 6, 8 and 10 had ranks 3, 4 and 5, but they all had the same magnitude. So according to our procedure for dealing with ties, the average of 3, 4 and 5 is 4. So each of these 3 patients is given the rank of 4. Patient 6 had a negative sign, so their 4 goes in the negative sign column. Patient 8 had a negative, they go in the negative sign column as well, but patient 10 had a positive sign, so their rank of 4 goes in the positive sign column. Patient 2 had a rank of 6 with a negative sign, patient 7 had a rank of 7 with a positive sign, and patients 9 and 4 had negative ranks as well. In that way, we've separated off the ranks of all those with a positive sign and all those with a negative sign. And then all we have to do is add up all the negative ranks. 2 plus 4 plus 4 plus 6 plus 8 plus 9 is 33. And add up the ranks with the positive sign. 1 plus 4 plus 7 gives 12. That's just like separating off the men and the women when we separated people by height. And we're looking to see, do all the ranks of the negative signs, equivalent to the women, appear down one end of the ranking, whereas the ranks of the positive signs, equivalent to the men, for example, appear at the other end. And that's characterized by the rank sums. If the null hypothesis is correct, then the sum of the negative and positive ranks should be about equal, because the positive and negative should be randomly distributed along the row, just like if our men and women were equal heights, they would be randomly distributed along the row when they were ranked. So we want to say, are the sums of 33 and 12 equivalent? Well, to do that we have to use some tables. We've got the sum of the negative ranks of 33 and the sum of the positive ranks of 12. If we add both of those together, that means the sum of all ranks will be 45. Remember, we started off with 10 patients, but we had one where there was a 0 difference, and we ignore 0 differences in this test. So there are only 9 left. And if you look in this table of the critical values for the one sample Wilcoxon's test, then for a sample size of 9, the expected sum is 22.5. Actually, that's a good check, because it must always be half the sum of all the ranks. So we got 45 the sum of all our ranks. 22.5 is half of that. That's a confirmation that we've got our sums correct. But if we look at this table, we're interested in a two-tailed test with a significance level of 5%. For p equals 0.05 two-tail, we see that the critical sum is given as 5 in this table. So we have to compare our actual sums of 33 and 12 with that. And the procedure says that we take the smaller of the rank sums. The smaller of 33 and 12 is 12. So we're comparing 12 with 5. 12 is greater than the critical value, which means that we don't have a significant result. Remember, the test here is the opposite of the normal tests. We only reject the null hypothesis if our rank sum is less than the critical value. Here it's greater than the critical value, which means it's closer to the expected value of 22.5, and hence it's not significant. So we can't reject the null hypothesis. So in fact, this data doesn't give us any evidence that the relative function differs from 50%. So that's how we can apply the Wilcoxon test to this type of data. It didn't involve any complicated calculations. It just involved putting things in order, so it's not too difficult to do this sort of calculation by hand.